Okay, let's, oh, sorry about that. Let's finish up this party with our last class, which is our final exam. And everybody know when the final exam is? Tuesday, 9:30 to 11:30. You don't even have to write it down. You'll just memorize it here, right? Tuesday, 9:30 to 11:30 in this class room. Okay. If you want to do it online, that's fine. Just let me know in advance. Let me know by Monday at 8, just so that I can make sure I get all the right copies printed out and all that stuff. The rules are you get 4 sheets, right? So you have one 8.5 by 11 for each exam, plus an additional one for the final. And so hopefully you didn't pitch your old sheets, because that would mean that you'd have to create another one. But you don't have to bring 4. You can bring up to and including 4. Yes, sir. I don't care. You can do what you want. You can create new ones. It's totally up to you. Okay. Same rules. I don't need to see a bunch of MATLAB scripting. I need to see you work. And then if you use MATLAB, that's fine. But I don't want to see just a bunch of syntax. You will not get credit if you just write MATLAB scripts. Okay. I've got to see the hand work, because at some point you needed to write the MATLAB script, and it would be most likely based on some of your handwork. So be mindful of that, I need to see what's all that you're actually going through your brains. You get 2 hours, so that's, depending on your perspective, that's a third less, or for the regular exams, you get 50% more, right? It goes both ways. So it won't be as in-depth or involved. Most of the questions will be very quick, not a lot of in-depth thought, but we will be touching each of the concepts. And so here are the concepts, right? We started out, whoops, why is this here? This is a different class. Don't say why. It's not the makeup exam. Stop it. Okay. Don't know why they did that. Sorry about that. All right. So we started off with phasors, because depending who you had or what you've had for introductory AC circuits, you may not have had any introductory AC circuits. So I know that the ECE department here is doing a better job of including some AC. So I'm not sure if that was with the class that you all are in, if they actually got AC. I know the predecessors had no idea how to do phasor analysis. And so we kind of did a review. It was a fairly quick review, but everything we do in this class is going to be focused on doing things from a steady state time invariant perspective. And so as a result, our voltages and currents have both a magnitude and an angle. And one of the things that I try to reinforce or stress at the beginning of the semester is make sure whenever you put down a response for a voltage or a current, it includes a magnitude and an angle, right? And I know a lot of the homeworks, there was only one or the other. So you got points taken off on the tests. It just seems like we, continue to reinforce that, because they are important. Unless you're being asked, what is the angle? What is the magnitude? Your magnitudes, your voltages and currents should have both. Okay. So when we represent a quantity in phasor analysis for AC circuits, we would do RMS quantities. So all the magnitudes are RMS, and we assume no DC offset. You can go back and forth from rectangular to polar or polar to rectangular. Should be able to do it in your calculator. There should be built in R to P or P to R functions. Or you can just use Euler's identity and go back and forth too, right? It's a right triangle, so it's not really hard to go ahead and do that. And speaking of right triangles, because our impedances in AC circuits land are all real or imaginary, there's no in between, we can go ahead and develop or utilize that right triangle to talk about what the power is, the power consumed, and I put consumed in quotes, because you don't actually consume reactive power, you borrow reactive power. That is the power that is sent back to the source at different times in the sine wave. So our right triangle has the real part, and that's always a positive number. This part here always, always, always should be going from left to right. So if you thought about this as an axis, that is the origin, and your P is always going to be in the positive direction because P is what dictates the direction of current. If you remember back from your circuit analysis days, that you always thought that current, was dictating. No, it's the actual power, because we talk about sources and loads and we say current is going into a load. Well, that means that the power is going into the load. So the current follows the power. And that's what really dictates the direction of current. So we have our power on the real axis. It's always positive. And then our reactive power is vectorially added to the real power to get the total power. And the reactive power can either be a positive number or a negative number. And it depends on the type of load that you have. If you have an inductive load, then that reactive power is going to be positive. If it's a capacitive, then the reactive power is going to be in the negative direction. And that gets to be cumbersome, talking about if it's inductive or if it's capacitive and what's the direction. So we throw all that stuff away. And then what we spent this semester is talking about things having a power factor. And it's a leading or a lagging power factor. So we talked about Eli the ice, and we no longer said Eli the ice. We actually expanded on it, and we talked about what current was doing. In Eli, the current is lagging the voltage. In ice, the current is leading the voltage. So you remember way at the beginning of the semester, I asked you what's happening with Eli and ice, and some people said that the voltage is lagging or leading the current. No, we always talk about what current is doing. Is current leading or lagging the voltage? If you do that, if you stay consistent with that, doing these power triangles is going to be hopefully a pretty easy thing to do. But still, at this point in my career, I still look at loads and think about power factors and what is the P and the Q. The total vector combination of those is the total or apparent power, and that has the value or the name S. And it's just the combination of the two. The units, watts, bars, and volt amperes, or VA. The angle between the real and the total power is what determines the power factor. And it's only because it's a right triangle, right? That's a trig identity. We know what SOHCAHTOA is. So we know that the cosine of that angle is the definition of ratio of real power to total power, or the power factor. So that's just the mathematical definition, just works out beautifully for us. So all of that stuff was hopefully a review. The first time we started looking at new material, I don't think many of you would have actually studied Y-bus, although you can build Y-bus at any point in your college career where you're studying circuit analysis and you can get results. But your Y-bus value is where we started, or building Y-bus was where we started to do it. And it really is just a process. A lot of what we're doing with power systems is we're trying to make a very consistent and standardized process so that we can take a lot of the guesswork out of it. We can have a computer do a lot of it. So write these down on your sheets, right? If I'm trying to build Y-bus, if I'm doing the self-admittance, I'm summing all the admittances connected to that one bus, right? With that being said, I need to make sure that I don't have any admittances in series off of a bus, because if I add those admittances first, I got a problem. So I got to add them in series before I invert, and then I can go ahead and add those in. That's the only little hitch, if you will, in this description here. But once you get past that, those are in series, and you add them as such, then you're in pretty good shape. The off diagonals are just the negative of the transfer admittances between any of those buses. So at this point, it should take you 3 minutes to do almost any size Y bus. All right. But again, it's so essential, because think about all the exams. On every single exam, we had a problem that you had to build Y bus. It's so fundamental being able to do power systems. So at this point, if it's on the final, you should be able to get hopefully a very quick, whatever many points that the problem is worth. Once you invert Y bus, then you get Z bus. And the diagonals happen to be the Thevenin equivalents seen by each of those buses. So remember when you were looking at circuit analysis and you were doing a bunch of series and parallel combinations to figure out Z Thevenin at a particular location or R Thevenin? You could do the same thing with Y bus and go ahead and spit out the results and not have to do any of that work. Makes it much easier, in my opinion, to do it. And then sometimes I've actually taught, how to solve for Thevenin equivalence. Just go ahead and build Y bus and do it that way. Most likely a newer topic. Again, it depends a little bit for when you've had circuit analysis. I'm not sure if you've covered three-phase systems in your previous circuit analysis, but in this class, we absolutely must have that because the vast majority of power is not only transferred, but utilized as a three-phase source. So all those motor loads, driving fans or conveyors or pumps or whatever, if it's a three-phase motor, which means most likely anything greater than between 5 and 10 horsepower, is almost guaranteed to be a three-phase load. Okay. So you might even be able to get 15 horsepower motor for like elevators in a commercial building. Like say you're in a doctor's office and you need to be able to get staff or patients up to the second floor. You need to have an elevator. So for disability, for people who perhaps maybe have disabilities. So that might be a single phase motor. But in other cases, it's much more expensive to go with that single phase motor. So we'll just go with three phase. So if you have a three phase supply, you'll just run it that way. So with that three phase adds a little bit of complexity because now we got voltages and currents that aren't equivalent to each other. We have line voltages and phase voltages and line currents and phase currents. And depending on the rotation, ABC or ACB, and that rotation just has to do with the sine waves and how they rotate along, then you actually get phase shift. So this is just a table that we put up in the notes, a long time ago, but this is the concepts of what we're looking at. So you should be able to utilize this table and figure out what is a phase and what is a line. If you're working with phasors, then that's the only time you see that you have the square root of 3. Every other time, you're going to be using multiples of 3. So for impedances, if you're going from Y to delta or delta to Y, you're going to use the multiple of 3. If you're going to go power is also going to be multiples of 3. We may sneak in some different voltages in there to convert things to square root of 3, but the base equations are all based on 3. And that's why in this here, you'll notice that equation, S equals square root of 3, V line, I line conjugate. I use this equation more than I use the 3 because you sometimes get confused. Are you talking line quantities or phase quantities? If you use this one that's that's written on here on the description, what you'll find is that you usually won't make mistakes because most of the time in industry, people are going to tell you quantities or give you quantities that are line quantities. So when we talk about a 345 kV system, that means that the line-to-line voltage is 345 kV. If I got a 1200 amp load, that means the line current going to that load is 1200 amps. All right? Those aren't phase quantities. They may be phase quantities, but in general, we're going to be giving you line quantities. So if you use that equation, you're already given line quantities. You can go ahead and do the calculations there. And then I add this thing because so many people mess this up. It's not really that common. But you have to be mindful. There is no such thing as a three-phase resistor, a three-phase inductor, or a three-phase capacitor. They don't exist. I have 3 resistors, 3 capacitors, or 3 inductors configured as a three-phase load. So I've connected them in Y or delta, at least from this class's perspective. And that's it. You cannot go out and buy a three-phase resistor. You can go out and buy a three-phase resistor bank, which means you've got 3 resistors kind of wired internally, but you cannot buy a three-phase resistor, right? I'm kind of harping on that because that's a very common thing. People just assume that that's a three-phase device. It's not. It's the same thing with a motor. Your motor that you connect, it's a three-phase motor, but if you were to pull out the wiring out of the motor junction box, you actually have 3 leads that go into the motor. So there are 3 independent leads. And again, you connect it in delta Y to go ahead and make the system. The only thing that is actually three-phase is your source. And even then, your source has three voltage sources that are independent, but then somehow they get connected somehow internally. So then you actually have a three-phase source that's referenced to each other. All right. So that's pretty important that we discuss that so we understand the three-phase. Transformers may or may not have been a review. Somebody was telling me in physics they actually cover transformers a little bit now too. I'm surprised that that would be the case, but it's usually a pretty specific device for our electronics or electrical circuits things, but transformers exist in mechanical systems. What do you think a gearbox is? Gearbox, if you're driving in your car, unless you have a CVT, then you have a four-speed, whatever. As you shift gears, you basically are just using different turns ratios in your transformer. Not nearly as efficient as an electrical transformer, but it's the same concept. So that's why somebody was saying in physics, they're starting to discuss transformers more because they're a lot easier to have an analogy than they are a gearbox. But a transformer, its whole purpose in life is to step voltages up or down as necessary to either increase or decrease current. Normally, we want to decrease the current so that we have less losses, but sometimes that's just not practical because we have a load that can only handle a certain voltage. But ideally, if you could run your loads at as high a voltage as possible, it'd be a heck of a lot cheaper to run with less copper. Think about your car and think about the amount of copper wires. Anybody ever watched the video on a wiring harness that feeds the car? It's like, I don't know, thousands of wires going from one end to the other. And so could you imagine if you could shrink the wires down? Even better if you could do things digitally, right? Have everything on a bus and then go ahead and address it that way. I don't know if that's going to happen anytime soon. But car systems are terrible because any serious load, you've got really big, expensive copper wire that adds a lot of weight. So if we could run at a higher voltage, then we would save a lot on copper costs. Doesn't work so well to use a transformer in your car because your car operates at DC. Transformers only work at AC. You can plug in DC to a transformer, but eventually that transformer is going to short out and not do any good for you. So transformers only convert AC from that higher voltage to a lower voltage and vice versa. And they are considered very efficient to the point where you actually don't have any power losses. And so oftentimes when I do fault analysis, when I do a calculation, I almost always will neglect the value of resistance because it's so small. Transformers operating at full load, 99% efficient. So that 1% loss of efficiency is usually not enough to get super, super worried about, I guess, unless you're trying to sell joules and you really need to keep track of every bit of loss that you have. To build a three-phase transformer, just like the case with the resistors, inductors, and capacitors, you take three single-phase transformers and you connect them in either a delta or a Y. Same thing. If you were to buy a three-phase transformer in one unit and you crack open the shell, there are actually three independent windings in there. And if I could ever convince the people at facilities to let me open the door or put a window in it, in the one that's right across my office, you'll see three single-phase can transformers. They look like transformer cans, and that's all the power for old barrels. It's right outside my office, basically. But those are three individual transformers. And so works perfectly fine. In some ways, it's actually better to do it that way, because if I have a failed phase, how easy is it to repair one phase? I can go buy a new can, or I have to replace the entire transformer because one phase burned up. You can do that practically up till about probably 225, maybe 300 kVA load, where you can just go off the shelf and buy a transformer. Like literally, if you said, hey, I need a 300 kVA transformer, I'd tell you to go down to the local electrical supply, not Home Depot, but like Gilman, and they can order three-phase pole-mounted transformers, and then you just put them where you need to and wire them up, and they work beautifully. And they're cheap. It's very easy. They're heavy, right? These things aren't light, but it's a much more efficient way than ordering a three-phase transformer from ABB or something like that. Here is our equivalent circuit model of a real-world transformer. It includes all the losses, both real and reactive. We have core losses, magnetizing losses, and then we have winding and leakage losses. And so this equivalent circuit would be fine if I asked you to develop an equivalent circuit for our transformer. Okay. You don't need to do all 6. You can just do the 4 that is shown. Transformers are great, but boy, oh boy, do they make the calculations way more cumbersome for doing electric circuit analysis, because every time I walk through a transformer, I reflect the impedance by the square of the turns ratio. And that would mean every time all those impedances that I have on one side have to be reflected to the other side, and then I could do circuit analysis. That is way too cumbersome. So we're going to do everything in per unit. Notice even in this description over here, you didn't see a lot of discussion about how you convert currents or even voltages or impedances. Because if I do everything in per unit, there is no conversion necessary. So doing things in per unit is really the only way to do systems analysis in a power system, because your circuit no longer has transformers represented as devices that step things up or down. They're just there shown as an impedance. And so remember the rules about doing per unit. Pick S base and only one S base. Pick one and only one V base. The difference between the S base and the V base is I've only got one S base for the entire system. For the V base, I have to convert that V base through all the transformers and step them up or down. So every time I go through a transformer, I have a different zone or region where that V base exists. Once I have that, then I can calculate the Z base in those regions just by using VB squared over S base, and I'm good to go. I can start going and converting and calculating all the things that I need to do. And then my final thing will just be a diagram with impedances, no transformers shown. You may introduce some phase shifts, but we're not going to worry about that for this class. Doing the phase shift stuff is usually more appropriate for when you're trying to interconnect different systems together, that there could be a potential phase shift between the two. You will note V base divided by S base, or V base squared divided by S base. Z base has to be a single phase term, because there is no such thing as a 3-phase resistor, inductor, capacitor. There's a theme here. Do you see how I keep talking about the same thing? So ohms is single phase, but voltage and current can be line-to-line quantities. Those aren't necessarily single-phase quantities, but ZB must be. So you have to be very careful about your V base and your S base to make sure the units work out that you're going to end up with a single-phase Z base. So either pick both phase quantities for your V base, single phase quantities for your V base and your S base, or pick a 3-phase S base and a line-to-line V base, and the math will work out because that square root of 3 gets squared, and then you have the 3's get canceled out. Very, very careful not to do that. If you purchase equipment or come across equipment, and again, this is the industry standard, they're going to tell you what the impedance is on a per unit basis. The per unit basis is the equipment ratings of the equipment that you purchased. So when you buy a transformer, 100 MVA with whatever voltage ratings you have, that's what that Z base is, that Z per unit is based on. Same thing with a generator. You buy a 100 MVA, 13.8 kV generator, all the impedance data is going to be given to you in per unit based on that 100 MVA and that 13.8 kV. Remember, we looked at 2 different data points. We looked at transformer tests, and we looked at a generator test sheet for Dolby, and we saw in both instances that we had our data was given to us in per unit and not in actual ohms. The only time you'll actually see ohms for impedance data is the transmission line, because you don't go out and purchase a transmission line from the local distributor. You construct it. So it's designed and constructed. So the impedances are all going to be determined based on the topography as well as your design. So you have to calculate it. And at that point, you're calculating an impedance. The transmission line has no idea what the voltage you're running in or the current. So you don't have an S base or a V base, because the voltage could be 345 kV or it could be 5 volts. It doesn't matter. The transmission line will operate the same in either case. So if they aren't on a consistent base, meaning the equipment you purchased has its original equipment bases, V base and S base. If those don't match your system that you're analyzing, V base and S base, you just got to convert it using this equation here. This is not a complicated equation. This equation is basically doing Z per unit old multiplied by Z base old, and then you divide it by Z base new. That's all this equation is doing. But it cleans it up a little bit, right? It kind of collects the voltages and squares them and does it that way. So if you don't like remembering this or you're not sure where it comes from, just go back and go from per unit to actual ohms on the original system base, and then divide it by the new per unit base so that you can get everything into a new per unit system. That's all it is. So it really is just using the concept of per unit, but putting it more succinctly. Okay. And that was pretty much it for transmission lines. Really, really, really simplifies our work to the point where everybody in the industry has to be able to use per unit. You got to be good at it. Transmission lines. This is when we used our pi equivalent representation, and we had a bunch of hyperbolic sines and cosines, but we've really avoided doing hyperbolic sines and cosines. We can, but for the most part, it's more efficient just to use the medium line length parameters. And you can see that I've written my ABCD matrix or network written as Z primes. But if for the most part, if you just substitute Z's and Y's for Z primes and Y primes, you'll probably be okay. But this is just a way to calculate sending end quantities given a transmission line with a certain loading and nominal voltage at the receiving end. So normally, that dictates what the system has to be able to provide. Because remember, they're the customer. They're paying the bill. So you better deliver them what they expect, which is a certain amount of current at a fixed voltage. And when I say fixed voltage, it's within reason. Over here, that's the utilities problem. They're responsible to adjust their system. And you as the client, I don't care. I don't care that you're having to be, 200% above your nominal value. That's your problem. You have to figure out how to make your system work. My problem is I'll pay you to provide whatever voltage I need and load whatever voltage I need, but I'm not going to pay you to fix your problems there. You've got to take care of that yourself. So systems are taking that into account and designing things that way. Now I'm being a little flip by saying, I don't care, 200%, that's your problem. Generally speaking, it doesn't get to 200%. I'm not saying it never does. I've never seen it. But for the most part, you're not going to see magnitudes changing by more than plus or minus 10%. That would be unusual to be outside that range. But still, the customers are expecting plus or minus 3%. So it's a lot tighter tolerance. And then the last thing we talked about transmission line is surge impedance loading. So if you have a lossless transmission line, you can estimate approximately what the surge impedance loading is and when the line starts to consume bars or absorb bars. And as long as your X over R ratios are fairly high, 30 or 40 or greater, then you can go ahead and you can use that concept, that surge impedance loading that says, yep, this is valid. Other than that, you can't necessarily do it because it's not a lossless transmission line. Then, like I said, we probably did the hardest topic. Maybe not. I don't know. Depends if you like math or not. But Newton-Raphson load flow was a lot of math, right? Because we don't have a really good way, other than graphically, to solve for systems that have nonlinear equations. So we talked about in power electronics, we do it all the time. You pick a Q point, a quiescent or an operating point, then you lock it in at small signal analysis, and then you go from there. That doesn't work here for power systems because we have too many things to see to be able to do it plausibly. So we grabbed the Newton-Raphson algorithm, which is basically a Taylor series expansion, and we stole it for our purposes. And really, this is just a bunch of equations. These are the only two equations, if I was taking the test, I would write these two equations generically. These are the two. I would not write, and these are our power balance equations, right? I would not write your Jacobian equations, your partial derivative equations, because to me, it's just as easy for me to go ahead and derive them. I find that it just gets to be cumbersome to specify what I is and what K is and go through all that. I just write these two equations, I simplify down, and then I'm reasonably comfortable with doing partial derivatives. I know it's calculus and we're not always a fan, but these aren't really crazy difficult derivatives to take, right? You might have a v squared and you might have a sine of an angle minus another angle or a cosine of an angle minus another angle, but that's pretty much it, right? Pretty straightforward derivatives that you're going to be doing. But what we do is we apply the Newton-Raphson algorithm to update our angles and our magnitudes for the unknown voltage magnitudes and angles based on iterating a process. And that process is going to determine, or we need to determine, I should say, what we are solving for. So you have to define that by specifying the type of buses, slack, load, or gen. And the whole reason why we spend so much time identifying slack, load, or gen is because we don't know which equations to write. And we don't know which variables to solve. So if we've specified the bus type, that should tell you what equations I need to write and what variables I need to solve for. Once you have that, it's really just, plugging and chugging this algorithm. It's not all that complicated to do. Okay. And that's it for Newton-Raphson. Then we talked about the different times and the generator when it experiences a fault, how that current is going to change. And it has to change because you have different sources of energy. You have energy that happens for a subtransient time, energy that happens for a transient, and energy that happens for steady state. And so each of those are modeled as decaying exponentials, just like we would in any first order electric circuit, an LNR circuit with a time constant. We do the same thing here, but we add it all up to include it in that one equation so that we can model what happens to the energy over the course of a fault. And that first little bit is when we have really high currents because we have a fair amount of asymmetrical current. And so those typically are our withstand capabilities of our breaker. So not interrupting, but withstand. So the first few cycles after a fault, our breakers, it's not fast enough to operate, but they got to be able to withstand the amount of current that they see. And then after 2 to 3 cycles, now the breaker might be expected or probably is expected to interrupt, isolate. And so it has to be able to interrupt. So you have breakers with interrupt and withstand ratings. So we just modeled it as an ideal source behind a bearing reactance. That's kind of the segue from number 9. Then we utilize superposition. Remember way back in the day when you were taught superposition and you're like, why would I do superposition? It seems like a lot of work when I can just get it directly. Well, we use superposition when we have a fault at a bus. We add in a fault source that is indicative of the pre-fault voltage at the fault location. And so all we're doing right here is adding in that negative voltage because we want to drag it down to 0. And then that's the concept of superposition. And so when you add in a new source, you no longer have necessarily current, but you have changes in voltage. That's the whole thing about superposition, right? You're going to go ahead and calculate what they are one at a time, and then you add them all up at the end. This one is solving for the change in voltages because we've done all the other ones, all the other voltage sources in there. We just have to add that one that's indicative of the fault. And our change in voltages are going to be determined by our Z-bus. So those Z's that you see here are just grabbed directly from Z-bus. Now you can calculate line flows. So any line flow, you take the differences in voltages and you either multiply by the transfer admittance or you divide by the impedance between the two buses. That's all it is. That's exactly what we did on the first homework and the first test. We just keep doing it because it helps us calculate the current. And then we moved into symmetrical component land, and symmetrical component land was we no longer have balanced systems. Our systems are unbalanced, and it makes it very hard to analyze those systems if those neutrals aren't at 0 volts. So we force them to be at 0 volts for two of the systems, positive and negative sequence. But zero sequence, we allow it to be a non-zero voltage because we've got to have ground current being able to flow, and that's what takes our zero sequence. So all we do is with our positive and negative and zero is we decouple our phasors into a set of symmetrical, not balanced, but symmetrical phasors. And how do we do it? Well, with the capital A matrix, with the fact that A is equal to, or alpha is equal to 1 at an angle of 120 degrees. Because the system is balanced, we can solve for positive or negative just by phase shifting appropriately. So we don't actually have to calculate those, we just phase shift them. The zero sequence are all identical to each other, so there is no calculation. Once you find one, you can find the other. And for what we're trying to do in this class, we will typically put these sequence networks together, solve for the currents in symmetrical component land, and then calculate what the phase currents are, because the phase currents are the actual fault currents. So we built some sequence network diagrams, and it was pretty easy for generators, motors, and regular old loads. They would have maybe a power source in the positive sequence and then the impedance, or just the impedance in the negative sequence. Easy peasy. But when we had a transformer, positive and negative sequence were the same. They were just impedances, but zero sequence was a function of can ground fault current flow. And so you really need to look at those diagrams to make sure, am I able to have ground fault current? So if the Y is there, you got to look and see what's connected to the neutral. If the delta is there, you have to see if there is a Y. If there is a Y, can the neutral current flow? If you get stuck with it, the whole thing about that is what flows in the primary has to flow in the secondary. So if you can't have secondary current flowing in the secondary, if you can't have zero sequence current flowing in the secondary, then it sure as heck can't flow in the primary. All right. So just to think a little bit about it, because that's the whole purpose of a transformer. It just steps up or down the current. And if the current isn't allowed to flow on one side, it can't flow on the other side either. Even if you think it can, it can't because it reflects an infinite impedance to the transformer. Once you've figured out all your sequence diagrams, you can build Y buses for each of the sequence diagram to solve for Z, and then solve for Z buses and get Thevenin equivalence. And then you can couple networks together, depending on the fault type. Single line of ground, take all three, put them in series with each other. Line-to-line fault, take positive and negative, no zero sequence because there's no ground fault current. There's no connection to ground, so there's no ground fault. So you put the positive and the negative, and you connect them together. So you put them in parallel. And for a double line of ground fault, you calculate, I'm sorry, not you calculate, you put the three networks together in parallel, and you do the calculations. Okay. And then you can do that for asymmetrical faults. You can take our superposition approach and expand it to those systems. But that becomes a lot more cumbersome just because of the number of sequence networks that you have to calculate and get to be really long. And here are the test questions. Figure out how to set a current limiting resistor sort of in the neutral. Pretty easy. If I give you some sequence element, positive, negative, and zero, can you calculate the phase components? Y bus, right? Still there, ain't going away because it's pretty important. Be able to do Newton-Raphson. And then state the variable. So again, more of a high level question. You get 2 hours. So I'm not going to ask you to do a 3-bus Newton-Raphson problem, right? that might take too much time to do during a 2-hour exam. I don't know, just saying. Maybe that should be the test, right? See how far you could get into doing a 3-bus Newton-Raphson with 4 equations and 4 unknowns and a Jacobian that's 16 elements and all that stuff. And force you to do it on your TIs, not use MATLAB. Doesn't sound real fair, does it? But yeah, being able to do that and then be able to perform some iterations on a really simple system. So a really simple system, right, might have no real parts, maybe all reactive, might have all the starting voltages at 1 at an angle of 0. If you start at 1 at an angle of 0, it makes the calculations a lot easier, right? Per unit, per unit, per unit, be able to do per unit. And then next one is a little bit of a mystery, but think about, when we talked about sequence diagrams, what would be the purpose of certain types of transformer connection? And that's it. I've been yammering away for 40 minutes. You're sick of hearing me talk? You can say yes. How about that? A lot of verbiage. But we covered a lot of material, right? And for most of you, this is probably pretty new. Those of you aren't even in electrical, it's like, what am I doing here, right? But hopefully you have a newfound appreciation of what's happening behind the scenes. And there's, some discussion as why this class counts as one of the renewable energy one. Well, renewable energy doesn't work if it doesn't tie to the grid. So unless you're going to, live like a hermit basically and have very little power capacity at a camp, although that's getting better and better, right? Because you can put batteries, it's still not very environmental if you got tons and tons of batteries and all that stuff. It's almost always cheaper, more efficient, and can be more environmentally friendly if you can connect to the grid. I said can be. That depends on the source that we use. So yeah, it really does help a lot because the more energy we can use over electrical systems, the better off we'll be. And this is not a put down on mechanical or chemical, but for the most part, and I know there's biomass, I get that, but I would imagine, I don't have any data to back this up, but the vast majority of energy that's transferred chemically is from fossil fuels because it's cheap. Hard to compete with something that's been processed naturally for millions of years, right? Whereas with biomass, you take a lot of energy and it doesn't have the same energy density, and there are other problems with it. That's why they have to put the warning labels on gas tanks. May contain up to 15% ethanol, which is a biofuel, right? It's from corn stock, I believe. But yeah, the grid, in my opinion, again, this is opinion, is going to be the greatest resource for a greener, more efficient, and more renewable energy source. I know EVs with the current, presidential administration, they've kind of lost favor a little bit. But if you go to China, 50% of their cars, new cars, are EV. Why is that? Chinese government is run by this communist government, and they tend to focus, not always, but tend to focus on what's the most efficient and best use for society. There are some cases that may not be the case, but they've figured out like, hey, Beijing 20 years ago was one of the most polluted cities in the world. Do you ever hear about Beijing and smog and pollution? Not anymore. So if you can do stuff with electricity, there's heat generated, but you're not burning anything. You still need the energy, and that's where the problem comes from, right? So what are the energy sources that we need? And then there's still battery technology, right? So a Tesla with big batteries, how does that impact the environment? It certainly has a lot of impacts. But the question is, how readily recyclable are there? I don't know about different, nickel cadmium or lithium ion batteries, how recyclable they are. But lead acid batteries, at least car batteries, are 100% recyclable. They recycle the entire package. I would imagine that is, if it's not currently the case, will be the case for newer battery technologies, because nobody wants to expose our or dump, hazardous chemicals. So the more stuff we can stay in electrical land, the better off we'll be. And if you don't like the look of telephone poles, you can put them underground. Not the telephone poles, but the wires. You can run all that power underground. It's no problem. Look at campus. Anybody here see telephone poles around campus? I don't know if they still do, but over by, where they're putting that new building by the Collins Center, if you looked in the parking lot back at the end, they used to, I haven't seen it, they used to have an overhead line there. But the rest of campus, I mean, our lights are on in this room right now, and you can look outside the building and you don't see any overhead wires. So that's the other thing, right? If it's ugly, you can make it less ugly. It doesn't make it cheaper, but you can make it a little more pleasant. That was one of the problems with the New England Clean Energy Connect, is it was going to spoil the beauty of the western part of the state with running an overhead DC line that was going to benefit not Mainers. To which I flippantly said, we'll just put it underground. And everybody scoffed and screamed and yelled because it would be so expensive. But you could have put that DC line underground. There are 345 kV lines all underground in New York City. Yes, sir. Got a question?
I was going to say, you kind of already said it yourself. Doesn't it become more difficult over really long distances because it's expensive, more expensive to come underground?
It doesn't make it more difficult. It just makes it more expensive, right? So it's the same technical process. It just becomes pricier. Going underground is more expensive. You got to drill, you got to dig, you got to use solid dielectric cable, or you could use what's called pipe type cable, which you take a pipe and you put the conductor in it spaced away, and then you run oil on the outside. That's like the most efficient type of cable, because you can pump the oil through and that keeps it cooler. But the problem is you need a pumping station every 5 miles, 10 miles. So that's not the best way to do it. But it wasn't that long ago, and you can still go in Long Island. And I've worked on projects recently that had a bunch of underground pipe type cable that would hopefully, take care of it. But you don't see that much anymore. It's going the way of the dodo bird. Question? I think they turn it on this month, right? I think it's on. It didn't get any fanfare, so they're probably trying to keep it on the DL just because it caused a lot of agita. But I believe it is. Other questions? Did you show up on time for class? Did we talk about that already? I will empower you to figure that out on your own. It's a pretty easy answer, but that was already discussed. Let's just say you won't have far to walk from your current spot. I'll give you a hint. Anything else? Well, for those of you, this is a sad day for me. For many of you, I probably will never see you again, because unless you're EET or take follow-on classes, I probably won't see you. So it's been good. I like having big classes of mixed students and all that stuff because it adds differences to the class and it really makes it enjoyable. Being a teacher, at least for me, a lot about it is the interaction. I really enjoy, I'm not an extrovert by any stretch, but I really like it when I get to not shape, but just help and be along and then answer questions, because we all have opinions and we all think we know what's right and whatever, but it's good to be a small, teeny tiny part of that. And so maybe in a year or two, you'll be like looking at a transmission line, and you remember sitting in this class saying, oh, what happened with Newton Raphson? I don't want to think about that again. But next time you look at your utility bill, maybe you'll be like, okay, this is $175. There's a lot happening behind here. And when you turn on your light and it's cold and your bathroom light turns on and you're like, oh, thank God for that class, because the material that people are doing keeps the lights on, keeps it running. And when you scream at the fact that the lights aren't working because the power's out, just remember how cheap you pay and how reliable the power is. So go camping sometime without power and see how difficult it is. It's easy sometimes, but after you go for a few days and you haven't had a warm shower, and you're eating your 17th can of, canned beans or something like that, it can get a little bit like, I miss the creature comforts of home. A lot of the creature comforts are there because of the energy that's supplied to us. But with that, let's be good stewards. Let's try to use that energy wisely. You keep the cost down for you, but it keeps the cost down for everybody. If we just think about, hey, energy's cheap, like right now, gas is what, 268 a gallon or something like that. It's incredibly cheap. That doesn't mean I'm going to drive down, and go and buy I don't know, 7 million liter dually, whatever, because eventually it's going to come back up and then we all pay for that. So just be smart. I'm not saying don't do it. Just figure out what your needs are and try to be judicious about your energy consumption, because there are trade-offs. The only trade-off is if you reduce your energy consumption. And there is a trade-off there. It's your comfort, right? Most days I drive to campus in my Prius without the heat running. My wife looks at me like I'm nuts, but it's like, I'm doing this because I'm trying to remind myself, like, this is, it's a luxury to have heat and all that stuff. And so when she's in the car, the heat's on. But with me, it's like I'm putting my hat and gloves on and just smiling with it. But just make good decisions. Be smart, realize your individual decisions impact us all. And that's not a political statement. That's just reality. All right. Have a great day. And I'll give you another hint for the exam. I'll see you on Tuesday around 9:30-ish. Not too far from this room. Take care, everyone. Have a great weekend.
Thanks, Paul.
Thank you.
Thank you, Paul. Have a good
Thank
one.
you.